we're going to build a nuclear bomb detonation switch. As you can imagine, the requirements on such a switch are quite extreme, and a simple mechanical switch will not be good enough. Now, the design they came up with to fulfill these requirements is quite spectacular, but before we go into how this switch works, we're going to talk about the Fat Man. I'm talking about this guy. This is Fat Man. Fat Man is a plutonium-based implosion type nuclear bomb. Fat Man is the bomb that was dropped over Nagasaki. It is one of 2 nuclear weapons used in warfare, so far, and it's the type of bomb that would use the switch we're going to build. Now, a nuclear bomb is not something you detonate with a simple blasting cap as you would with a dynamite. It is a bit more complicated. The design of Fat Man is kinda like a football, where each shape is a compartment that contains conventional explosives. And the pressure of the explosions in each compartment pushes down on a plutonium sphere onto a neutron initiator. And once the plutonium is compressed around the neutron initiator, fission occurs. And fission is where neutrons start splitting atoms in a chain reaction, releasing immense amounts of energy. Now, if the timing of these detonations are not correct, let's say that this side detonates before this one, you would get an asymmetrical compression of the plutonium, and you could get something that's called a fizzle. And a fizzle is where only part of the nuclear fuel is detonated, resulting in a much weaker explosion, and the rest of the nuclear fuel is just scattered from the initial explosion. So let's go through the problem. We have a switch, and we have the detonator. Between them we have a cable, and ideally a cable is a conductor with 0 impedance, but in the real world that doesn't exist. So a cable actually looks something like this. A cable is essentially an infinite amount of LC filters in series. That means that whatever comes out of the switch is not necessarily the same that reaches the detonator. Now, with proper cable design you can reduce these parasitic properties to an acceptable level. The problem that remains is the switch. Now, ideally you would have a switch like this with no parasitics, but the switch itself is an inductor. So no matter how much you reduce the inductance in the cable, you still have the inductance in the switch. And apparently you can't reach an acceptable inductance in a mechanical switch. And therefore mechanical switches cannot be used. So what effect does this inductance have on the energy transfer to the detonator? Well, here you have the capacitor that stores the energy that is used to trigger the detonator. So when you flip the switch you will have a very sharp energy pulse at this point. But because of the parasitic properties of the cable and the switch, you will get something that looks more like this at the detonator. And that's because these are essentially a bunch of low-pass filters in series. And exactly how this curve looks depends on the length of the cable and the temperature and a bunch of stuff. So you simply can't be sure when the trigger occurs. So what we need to do is reduce the inductance of this switch enough to make sure that the time difference of the triggers between all the different detonators is less than 1 microsecond. This is the solution. This is the patent for the type of switch used in Fat Man. Now, this patent claims that this switch can trigger all the detonators within 0.5 microseconds. It was invented by Donald F. Hornig and the patent was filed in 1945. Here we have an illustration of what the switch looks like. This is viewed from the side and this is viewed from the top. And here we have the schematic that we're going to use to build the switch ourselves. So this is a spark gap type switch and the central component is this spark gap tube. So this tube is filled with an ionizable gas such as nitrogen, argon, neon, hydrogen or krypton. And you close this switch by ionizing the gas inside, allowing current to flow between the 2 main terminals. If we look at the schematic, here we have the capacitor bank that stores the energy that is used to trigger the detonators. These capacitors are recommended to hold a voltage of between 5000 and 15,000 volts. And the energy in this capacitor is used to create the spark inside the spark gap tube that ionizes the gas and closes the switch. And here you have a switch that initiates the spark. And this can be a mechanical switch. When this switch is in the off position, you can see that this capacitor is charging through this resistor. And then when it's in the on position, The capacitor is discharged through this transformer. And this transformer increases the voltage on the trigger pin of the spark gap tube, which causes a spark that ionizes the gas inside, closing the switch. These resistors are intended to have the same value, so you can see the secondary winding of this transformer is centered around half the voltage of the reservoir capacitors. And to make sure there are no voltage spikes here that causes the switch to trigger, there is a bypass condenser, as they call it. So as this mechanical switch is triggered, this capacitor discharges into the transformer that causes a spark in the spark gap tube that ionizes the gas inside, that allows current to flow from the reservoir capacitors into the load, that is the detonators. If we look at the mechanical model, here is the reservoir capacitors, which is connected to this terminal, that is in turn connected to this terminal in the spark gap tube. And then here we have the trigger pin, and this terminal is connected to this outer part of the cylinder, which is in turn connected to the detonators. So once the trigger pin causes a spark in the spark gap tube ionizing the gas, current will flow from the reservoir capacitors into the first terminal, through the ionized gas to the second terminal, through the outer part of this cylinder, and into the detonators. So this is what it looks like from the top, and as you can see, all these are to be connected to the detonators. And all the detonators connected will be triggered within 0.5 microseconds. So we're doing this the old school breadboard way. So the capacitors we're going to use are these high voltage microwave capacitors. And for decoupling we're going to use this film capacitor. These are about 1 microfarad each, and this is about 22 nanofarads. The capacitors will be charged to about 2000 volts. I hope that will suffice. And to charge it we're going to use this microwave transformer through this diode. And we're going to use 22 mega ohm resistors and one 10 mega ohm resistor. Now for the transformer to create the spark, I'm going to use another microwave transformer. Now this is not built for such a high voltage, so it might not work, but we will test it. So what will probably happen is that there will be some sparks between the wires of the windings, because the voltage is too high, and that could damage the transformer. It could melt the coatings on these wires so that they short. But since it's just one pulse and not that much energy, it might suffice for demonstration purposes. Okay, time to start populating it. Let's start mounting the larger components. Here we have the microwave transformer to charge the circuit. And we will charge the circuit through this diode. Now for the spark transformer, we'll place it here on the other side. So here we have the actual spark gap switch. Let's take a closer look at that. So the spark gap switch consists of 3 terminals, 1 trigger terminal and 2 main terminals. So the idea is to momentarily charge this trigger pin to a very high voltage, which will create a spark to the nearby terminals, ionizing the air and thereby allowing current to flow through the main terminals into the load. Now the only thing that's missing is the switch that will discharge this capacitor through the primary winding of this spark generator transformer. For the trigger we're going to use this plastic box. Now there is one more thing we're going to do before testing it. We're going to attach this fuse as the load. Now the goal will be to blow this fuse, because that would mean that we have successfully closed the circuit and detonated the nuclear bomb. Okay, it's ready for testing. So we'll connect it to the mains voltage to charge it. Let's see if anything blows up. Okay, so apparently those resistors cannot handle 2000 volts. Okay, so we're going to make a resistor out of several resistors in series. So to replace the 22 mega ohm resistors, we're going to use 7 3.3 mega ohm resistors in series. I ended up using 8 resistors instead of 7 because it will be easier to mount them. The exact value of the resistance is not that important. And I will use the same resistance value for all the 3 resistors. So now the voltage drop of each resistor will be 1/8 of the total voltage drop across the entire resistor network. Okay, let's remove the leftover resistor fragments. Okay, I think we're ready for another test. Second test. Okay, so the test was a failure, but we're on the right track. So what I think happened is that a spark formed in the spark gap before we could trigger it. So I think we will have to space the electrodes apart a bit more, so that we can control the actual detonation. Okay, now the fuse has been replaced. Let's make the spark gap a little bit wider. Okay, third test. Oh, no spark yet. Let's press the switch. Bombs away! Now unfortunately it did not ionize the air all the way across the gap, so there was no current going through the load, so we'll have to adjust the spark gap once more. Fourth test. Apparently we did not blow the fuse, so I guess the arc was actually just between the trigger and the first terminal. Let's adjust it and do it again. Okay, fifth test. Now we only got a spark between the trigger and the second terminal. So as you can see, there is not enough energy in the trigger pin to blow the fuse. The energy needs to come from the capacitor bank. Let's adjust it again. Test number 6. Test number 7. Test number 8. No. Test number 9. The nuclear bomb has been detonated. I have to say I'm quite surprised about how well this project went. I thought it would be much trickier to get high enough voltage on the trigger pin, but apparently this microwave transformer did the trick, even though we're way above its intended voltage range. I did see some arcing in the windings, which is to be expected, but apparently it did the trick anyway. And I thought it would be much harder to get the current to flow through the spark gap without a proper spark gap tube, with a more suitable ionization gas than air. And even though we're about 3000 volts off the recommended value, these 2000 volt capacitors were apparently enough for demonstration purposes. Now to conclude with a little more history, this triggered spark gap concept was not actually invented to detonate explosives. It was invented for photography, more specifically nighttime aerial photography. So when the United States Air Force were taking pictures, they had to light up the entire area to be photographed. And to do that, they had a bunch of huge capacitors weighing over 200 kilograms that were to be discharged into the flash tube. And to accommodate this extreme amount of energy to be transferred, the triggered spark gap was invented. And during the Manhattan Project, the triggered spark gap was repurposed to detonate explosives. And apparently it was very well suited for that task because that is how it's still used today.